Hi, welcome everyone to our panel on dataset management and kind of why dataset management is essential to building successful ML operations. Without the automation of data quality, MLOps can fail even when the rest of your pipeline is really well thought out. We want to learn a little bit more about how different companies prioritize and improve their collaboration to improve their dataset quality, model debugging errors, and just building better models in general. I'd like to introduce our panelists today. So, Alessya.
Hi, my name is Alyssa. I'm the CEO and co-founder at WhyLabs, the AI observability company, and I'm really excited to be here to discuss dataset quality.
Welcome to have you. Thank you so much. Chun, would you like to go?
Hey everyone, my name is Chun, currently head of product at Unfolded.ai. We just joined the Foursquare, and we are a geospatial analytics and visualization company. Before this, I was at Scale, and before Scale, I was at Uber.
Thanks. Nice to see you again. Adrian, would you like to go?
Hi, my name's Adrian Macneil. I'm the CEO and co-founder at Foxglove. We are a visualization and data management company for robotics and self-driving. And before that, I was the director of infrastructure and developer tools at Cruise.
Very nice. And last but not least, Ville.
Hey, my name is Ville Tuulos. I'm the CEO and co-founder at Outerbounds, where we develop Metaflow, which is an open source project we started at Netflix. So prior to Outerbounds, I was leading machine learning infrastructure at Netflix.
Awesome. Thanks so much, everyone. And I guess to get started, one of the things that's really common across a lot of ML operations and different companies is working with a lot of really varied and different data types. So I wanted to kind of throw an initial question out there is like, how do you manage kind of the ingestion and working with data when your company can be working with computer vision and audio and text and LiDAR and all these different data types at the same time?
Yeah, I think that's something that we see a lot of, and especially in the self-driving and robotics industry. There's, you have this kind of multimodal data. You're recording camera images, LiDAR point clouds often, and then, other data that may be happening on device, often, audio radars. And I think, it's important to look at both how you're kind of recording that data in the first place on the device, and in such a way that you can easily align between camera images and point clouds, for example, and have a record of exactly the timestamps that those are coming in, and then have that flow through into your data storage and your data lake. So yeah, that's something that's very important. I think I can kind of go into more detail if you want, but it's something that we found very important at Cruise and something we see a lot at Foxglove.
I guess one quick follow-up is what are kind of what's two different data types that are really hard to synchronize and work with at the same time, or two that you have to have special care around?
Yeah, I think so. It depends a lot on how people are approaching this problem. So we've noticed, for example, chatting to different companies, let's take LiDAR point clouds and images, for example. Many companies, well, there's different ways of approaching recording images, and we see some companies, especially ones that have kind of come from a ROS background or using ROS, the robotics framework, where often they will be recording image data as individual frames. And so that makes it actually relatively easy if you're recording individual frames of images and individual frames of point clouds, and you have timestamps on those. You still need to deal with aligning the timestamps, but at least you have a complete image and a complete point cloud. However, what is common, especially again in the AV and robotics industry, is to record images as actual video feeds. So H.264, for example, and we've come across a lot of companies that are recording H.264 or some other video encoding on their device, and then coming back and realigning that can be quite challenging. For those that are unfamiliar, if you're using a video encoding like H.264, you don't have a perfect frame. Every individual frame is not recorded. The compression is using elements of previous frames, so you actually need past data from that stream to be able to even regenerate a frame at a single point in time. And then, if that is getting recorded to literally a separate file on the device, then, it's much more efficient space-wise, but it makes life very hard for you when you're coming along and trying to realign those with point clouds, and you want to know other metadata, like the exact second that particular frame was received. So what we've seen people do in that case is actually record a separate channel of information. Again, it depends whether you're saving things like in a ROS or in protobufs or something like that, but they're storing kind of a separate data channel, which is keeping timestamps and other information that's needed to draw a parallel between an exact frame in your video feed with a point cloud. So that's one, I guess, where I've seen, it can be very easy, it can be very hard, but you have to make these trade-offs between how much space you're using recording wise and then, matching it up later.
Awesome. And Alessya, for WhyLabs, you're working with a lot of different types of data to make it observable. How have you built the product to deal with that from the beginning?
One of the things that we do to accomplish that is focus on reducing dimensionality. So specifically what we capture from different data types is various summary statistics and metadata. That allows us to kind of standardize across, going from images to video to audio files. So for instance, kind of the simplest idea is to capture metadata over time from all the devices that have been streaming or collecting data, and then watching that metadata as it evolves from day to day. That would help you, that very simple thing would help you identify when you have new types of devices introduced, new resolution introduced, or new video encoding formats introduced.
So with Metaflow, I know it's something that you guys have been building from the very beginning to scale up to basically any data type like a large tech company could want to handle. Is there anything special that you had to build in from the very beginning to handle that?
Yeah, that's a good question. Obviously, Netflix has a lot of tabular data, a lot of structured data, as well as a lot of unstructured data media in different formats. And definitely, I mean, the media encodings are an interesting question, like as Adrian pointed out. Now, it's an interesting question, how much different data types can be unified. I mean, quite factually, we have had different data paths. For different media types, we had a different data path, for videos, images, and then tabular data. Now, metadata management is definitely something that you can unify, and we had somewhat consistent ways, although I mean not perfectly consistent ways of handling metadata, across different data modalities. So, but yeah, I don't know to which degree everything could be unified, but at least these major categories you can define best practices to each one of them.
And so when people are building up kind of storage and data access systems, are you focusing on trying to unify data at kind of a raw, the way it's recorded level, or is there value in kind of lifting it and trying to do the unification at some embedded feature level or some compressed level? I think Alessya mentioned working with sufficient statistics and trying to do the comparison at that level.
I think from the geospatial analytics perspective, usually people are using timestamp is kind of the core to connect different data and different data formats. But the one thing we heard a lot, or working across the AV space and also ride sharing space, is we use geospatial location as kind of the major key to connect all the information. So at least for our company is the way unification works is we assign our key to each geospatial locations using our H3, kind of a framework, indexing framework, and then we put all the timestamp there. So us in the future can be easily kind of aggregate or join all different data based on your geolocation. So it's combining space and combining time and location, that you can have better concept about how the correlation between the space works.
Yeah, I agree with that. One thing I would add is that I would draw a distinction between when you're first ingesting data. You're bringing in, and again, maybe this is more specific to the AV industry or robotics, but you're ingesting data, and I would typically advocate for keeping it as close to the raw format as possible, and ideally in some kind of very standardized container where you have you can do this with a container format where you're keeping track of timestamps and like channels or topics that you're keeping data from, and keeping it as close as possible to the raw form. But one thing that's really important there is make sure that you in that raw form in your data lake or whatever you have, one thing that's really important is making sure that you're keeping message definitions that are required to actually decode this data. So if you're using protobufs or something, it's important that these files are kind of self-contained and they've got the definitions that are required to decode that, because those tend to evolve over time. Same thing if you're using ROS or ROS messages, you want to keep that over time. And then you have that base to build on, and you can create libraries or abstractions that make it easy for people to access that raw data in jobs, and then bring that into a kind of more structured, because the raw data also tends to, the schema tends to evolve a lot over time. So you want to be able to have, post-processing jobs which are taking that and transforming it into more structured data in your data warehouse, or, as it moves along to a feature store and things. And that's when, it'd be really good to be indexing on things such as geolocation and making it easy to find, in a structured format that changes less frequently.
Yeah, I guess building off that point, a lot of people when they start out, they're recording their data to hard drives and walking around between the team, handing out hard drives, or they get an S3 bucket that everyone shares and dumps data onto. I can see a lot of people have done this before. Like, how should people think about how to store their data for discoverability, to understand what's inside of it, to make it easy for like multiple different people to use at once?
Yeah, again, this is something that we sort of offer as a product, but advice I would give to anyone building a system like this is make sure you're recording on device, that you're recording along with every kind of file that you're recording should ideally be self-contained with everything that's needed to decode it. So if you're recording in protobufs or ROS messages or something, you've got those definitions. Have a structured ingestion process. So it's fine if you're recording to a hard drive or something on device. Some people record locally and then use a Wi-Fi offload. Some people record locally and then literally sort of pop the hard drive and ship it somewhere or carry it somewhere. But make sure you build a structured ingestion process which can take that data, again, possibly transform it. For example, we recommend actually on ingestion splitting these files up per topic or per channel. Typically you kind of see, especially in ROS-based systems, but quite often in robotics, you see people just kind of recording like all the topics into one file, which is great on device. It's simple, easy to reason about, but when you're storing it long-term, you want to make it more efficient to access. So you want to be breaking this up based on like different channels or topics, maybe breaking them up into smaller files based on timestamps. You can even go as far as keeping kind of a secondary index on, what data is contained in which file and where, and adding additional metadata like locations or certain kind of test conditions and things like that. And then, again, as I mentioned, build a library on top of that so that people can access that data. There's different ways of achieving that, whether that library is something that, hits an API to request, give me, certain time range, certain topics, certain events that I'm interested in. Or even a more simpler thing is just having all of that in a SQL database and having people query that directly, but have kind of a structured way for people to access that data and then be able to transform that into more interesting formats that are useful for training or labeling.
I would add to that a good practice that we see occasionally in organizations that have a lot of data is investing into some kind of data cataloging solution or approach. It really depends, like the implementation and the solution depends on what type of data you're working with and what type of problems that you're solving. But in order to improve discoverability, it really helps if there is some kind of very structured and easily queryable location where you can learn what kind of data you have. It would be even better if you have some sense of the quality of that data, because oftentimes what's frustrating is you start, processing and writing some kind of feature processors on the data, and then 3 weeks later you discover that there's just a schema that doesn't match and lots of missing records, and you basically wasted 3 weeks. So what becomes important is keeping some kind of meaningful cataloging of all of the data that you have.
Awesome.
Yeah.
I see everybody smiling. Sounds like resonated with everybody.
Yeah, absolutely. Even I would add to that actually, to the extent that you have data pipelines which depend on some schema, and that schema is something that's happening on your device, especially again in the AV or robotics industry, but probably parallels apply to other industries. Catch those regressions as early as possible. I'd even go so far as to say that if there's like particular schemas or topics or things that are getting published that are going to like potentially break a data pipeline, put those further upstream in your CI, even in the build process for creating your primary software that's generating these messages. Just put kind of a check there and say this schema has to be like this, otherwise fail the check, and just fail with you can just very simply say like if any of these files change, fail your CI, and with a message saying please come talk to us. It can be very, very simple, but like move that as far upstream as possible so that you don't find out either like getting paged in the middle of the night because something broke, or find out 3 weeks later that it's been silently failing for sure.
Specifically on like the on device logging, I think one thing that really important is like always logging the device version because it's like every week the device like keep updated, and also as well as the all the ML models and also like software in general. So people like it's really hard to like read the message across like different versions. It takes a lot of effort for one person to think about like, oh, maybe in the next like 10 version this message can be readable across the entire time. And it's just like really hard to do. I guess like especially for a larger team, like always logging like what is the device ID, device version, and at the same time who's the one recording it, and then is this like human behaviors or is this like car behaviors. So just like adding all the metadata there, so at least anything that happened, and or when you want to go debugging, you can find exactly the thing that you want to focus on.
I see this come up quite frequently in medical devices problems. Again, not recording the device oftentimes surprises during the deployment because then you lose a little bit of the control of what's the resolution, for example, of X-rays that you're capturing, and you deploy out the model, and if you're not keeping track of the devices, debugging that kind of drift is really frustrating. And what you brought up, the interesting point of like who is capturing the data also becomes very important. There's one organization that we worked with that was developing devices that would capture ultrasound images. Handheld ultrasound device would capture images, and the quality of the model really correlated with who was capturing. If the person was properly trained, the model would do really well, and if there weren't, the model would do very poorly. So if you're keeping track of that, that would make debugging a lot easier.
And maybe one more boring thing that I would like to add is that if you think that you have any kind of issues with data governance or data privacy, also like making those distinctions upfront, because like when you have a big data lake of 10 petabytes of data and you realize that actually we have to distinguish with some like a personal, like kind of a personal information or not, and like you have to scan through everything again and like recategorize everything, that can be quite painful. So if you have any inkling that like what might be more sensitive and what not, I mean, definitely makes sense to make the distinction upfront.
Yeah, makes sense. And how much of a role should machine learning itself play in like people's ability to search or pivot or break apart the data that they're working with?
That's a interesting question. I can take a stab at that. I think the answer from my perspective would be it really depends, because I would if you can, I would start, especially for discoverability. I would start with something very stable and statistically simple. So you could, explain if you're extracting some kind of metadata or statistics, it should be really easy to explain and really easy to reproduce. But of course, doing some sophisticated kind of dimensionality reduction is absolutely a best practice, like things like TSNE and UMAP. And then doing some kind of, visual similarities potentially for cataloging might be interesting. But I would say always start with something very simple.
I remember one thing we were working at when we were at the Nucleus was the similar image search, visual search of similar images. It's just a really like easy way for you when you have like small data set and you want to find like more similar data from like open data sets. It's at the same time, it's very efficient. But I guess like back to the question is like how much. It's also like very dependable. Like if you're like answering the wrong question, I don't see like having a larger scale of data gonna help you with that. But if you are like solving very specific, like Alessya said, then start small and then using all the like ML powered search and to help you like speed up your process will be like really smooth and just amazing.
Another thing I would add, I guess, is that don't jump into ML discoverability until you've done some of the basics around just metadata that you could be cataloging that you already have. So an example from the self-driving industry would be, you have all of this data and you can be very easily annotating it with things like properties like, is it raining? Is it daytime or nighttime? Are you in an intersection? What kind of maneuvers are you currently making? Are there pedestrians around? Are there cyclists around? Are there pedestrians within, 5 meters of the car or something like that? And you already have all of that information from the models that are running inferencing on the device, on the vehicle. So you can very easily be logging those and adding metadata to make, your kind of core data lake very discoverable. And you don't need to jump into kind of ML discoverability around your raw data sets, at least, because that would be a huge amount of data to be processing.
And I guess to that point, like, how much should the way you're storing the data, like, already know some of those kind of derived metadata? For example, like how many pedestrians are on the car. It's very easy for ML engineers to start adding more and more and more derived features versus like having the search and the ML infra be able to compute that on the fly. Yeah,
it's not super kind of resource intensive if you calculate that kind of metadata on ingestion, because on ingestion you're already essentially doing one loop typically through your entire data set. If you're transcoding it into a different format or even repacking it into different container formats and splitting files and things like that. So you're already doing a pass over your data. You certainly want to avoid the number of, just for the purpose of minimizing your compute costs, you want to avoid the number of passes that you're doing over data on ingestion. But if you come up with metadata that you agree is important, log it in a structured way into a metadata store and have references. It's pretty easy to keep kind of annotations of metadata over particular segments. Just any period of time you can have either like booleans or key value pairs where your number of pedestrians or an intersection or an enum for weather or something like that.
For designing Metaflow, one question I wanted to kind of dive into is how much did you take into account kind of more meta learning models where you're trying to do weak learning or kind of model in the loop training and storage and things like that?
Yeah, well, I don't think that like we are super opinionated about it. So I think that there are definitely valid use cases, and like if that's what makes sense for your use case, like go for it. I don't that like we did anything like really special. So like we were concerned about like really the kind of the data layer at the kind of starting from the very like fundamental questions like data discovery, like how do you access data quickly, and like of course like overall like the versioning, the experiment tracking, and so forth. And then like these questions of like how do you actually want to use data then to be quite project specific. So it really depends.
And what about the idea of like bringing compute to the data versus bringing data to the compute? Like, how important is that when people think about designing their machine learning systems?
Yeah, well, I can quickly start with that. So that's actually a really interesting question, because I know that it used to be maybe 10 years back when everybody was using MapReduce, like the kind of definitely the idea was that you bring the compute to data, and that was the kind of the prevailing paradigm at the time. Now, like if you think about the cloud, I think like what we are seeing is that we take a bit of a hybrid approach, that definitely you do want to take the compute pretty close to the data, basically meaning something like the same region, let's say in the cloud, in AWS. But then like you definitely don't have to couple data and compute on the same box. And I think that like being able to decouple data and compute is actually really powerful. So you want to be close enough, but it doesn't have to be physically exactly on the same device, on the same server. And I think that's a pretty powerful paradigm overall.
So kind of changing topics a little bit, I want to kind of get into some of the model debugging and kind of how people should think about using their own data when debugging ML models. So the first kind of thing to dive into is when someone's sitting down and not getting the performance they want out of their model, like where's the place they should spend their time? Is it looking at the model level itself? Is it looking kind of summary statistics like F1 and confusion matrices, or is it diving down and looking at like specific instances of the data itself?
I can jump in here maybe. So I would say the first question I would ask when you're trying to figure out what to start looking at is what changed? What do you suspect has changed in order to potentially cause the performance to change? So if you're running inference and production, there are various things that you can kind of suspect first and rule out. So if your model hasn't changed, if your hyperparameters haven't changed, then potentially if your feature pipeline hasn't changed, then I would start looking at the data because likely you're experiencing some kind of concept or distribution drift. If you're experimenting and iterating on the pipeline, then or the model architecture, then the type of debugging things that you'd want to do would be very different because potentially, again, if you're iterating continuously on tuning and hyperparameters, I would start there with really careful cataloging, or if you're changing your data pipeline itself, feature pipeline, like debugging that becomes very important. So it really depends on what's staying constant and what's changing.
Something that might sound obvious, but when especially again in an AV context or robotics, we have multiple models that are all interacting and you're shipping those to production. Often, getting enough metrics to be statistically significant immediately, again, sort of before you even land a model in production or merge a PR or something, getting metrics to prove that it has actually made an effect can be really difficult. You might need to be driving thousands of miles or something. So yeah, I would say that it's really important to make sure you actually have a good solid process for how you're validating and landing changes to models, individual models, and the interaction between those different things. Before you even are getting things into production, ideally, if you can get simulation and things like that are confidently predicting performance of on-road driving before you merge it. Because otherwise, you'll find yourself in a position where you're kind of complaining that it's a month later and some metrics have degraded, and meanwhile half a dozen models have changed. It's even a bit premature to start looking around at like, is there a problem with my data set or something? It might not even necessarily be one model's fault or the other model's fault if you have the interaction of several models causing behavior.
Debugging tools are always very fun to design because everyone's debugging workflow is just so different. And then the way I was always thinking about is from model-centric debugging versus a data-centric. So at ATG we have this data-centric debugging, which is we visualize all logging of human events and car behaviors. And at that time, you also see kind of how the camera image capture the look different than the real raw data log there, and you can drive guesses around what might be wrong there. So that's one way of building a lot of visualization tool to come up with a good solution of debugging and simulation with simulation imaging, or debugging with geospatial analytics based on different data formats. And that's for data debugging. And then at the same time for model debugging, one of the open source tool I was working at is called Macneil. So it's more like a model performance level debugging, but at the same time a feature level. So if you figure out my model A is performing better than B, I want to look at the beam more, and then kind of like segment the feature and also data set into like smaller batches, and to find like, oh, which feature might contribute to this set of the bad performance there. So this is kind of like just like two like aspect when I think about debugging tool. But like, I don't know, I think in the ideal world, everyone should like be very easy to jump between different approaches, and hope we can have like a unified way or like better playground for all the ML engineers to easily debugging with their different approaches.
Yeah, and like maybe to kind of a plus one what Alessya was saying before about like looking at the deltas and changes over time, and like with that, like really understanding all the sources of changes that can leak into your models and pipelines. So if you don't have really well-defined processes and infrastructure, it's easy to have like really like a surprising elements. I mean, like starting with the fact that, let's say, if your libraries change and suddenly somebody updated the version of the optimizer and you are getting different results, and technically the models are the same, the data is the same, but I mean, someone just changed the optimizer and like maybe you didn't notice that, and like suddenly the results change. So having a very controlled setup, like where you can control like kind of everything in the environment, and then you know that, okay, now the only thing that could have possibly changed is the data, or the only thing that could have possibly changed is the model. I mean, that makes things much more sane than like trying to kind of fly blind.
Yeah, lineage is critical there, I guess. You really need to be able to say, you know, this sensor data that we recorded, this driving on the road or whatever it is, led to this extraction that happened, you know, went into this labeling, went into this feature extraction job, went into this training job, and then, you know, this is where that model came from. Otherwise, hey, we've got this model running in production and no one can explain. You know, it's better or worse, doesn't matter if no one can kind of say what data that model came from.
So, and I like this idea that like every single ML engineer's workflow is a little bit different. And so one question I'd love to ask is like, what piece of the ML workflow is kind of missing or really underserved right now in terms of like working with your data or understanding how machine learning models work?
I think that there are two gaps there from talking with different stakeholders. First is like the way ML engineers come up with metrics is very different than the business in general. So like for one example consider there is like if you want to recommend someone to like, I don't know, purchase a product, then the ML engineers like the metrics might be, you know, like very, very specific and technical, but the business side will be like, oh, I just want this person like to purchase this product in like 2 seconds. So there's like a gap between like coming up with like good ML metrics and business metrics. And I feel like there's like, there should be like an individual voice there or like third party to combining saying like, oh, if I hit this ML metric, I have like an 80% chance of hitting that business metric. I'm still trying to figure this out, but I think that's a very interesting thing to think about. I think another gap is like working in different companies. I always find like data platforms have also kind of like gap with ML platform. So like ML platform or the ML products that we're trying to build is like, we always think about like ML workflow. And then once you start like debugging the data or see like what can be run across the data world, you just can't find like all the metadata you need about the data to debug your tools, debug your models. So like what's the best way to like using data as the core to design a flow across like data platform teams and also like ML platform teams, and have all the tools that talk really well with each other. And at the same time, like with like operations, like what is the best way to operation team to say like, oh, I think there might be something run, or like your model is not performing well in this segment of this street in the city. How this message should be recorded and then interpreted by the ML engineers. This is also another gap there. I think like ideally there should be like a tool or like a more opinion product there to solve these questions. And I definitely believe ML engineers or ML ops or data scientists will be the really like strong piece in filling these gaps.
Yeah, absolutely agree with everything that Chun said. And I would anecdotally say, talking to a really large number of machine learning engineers, one of the hardest questions that they need to answer every day, and it's always a surprise to me that this remains to be one of the hardest questions, is like, what was the distribution of my data yesterday, or what was the distribution of my data last week? Is it different from the distribution of my training data? Like fundamentally for machine learning systems, it's such an important question to answer. But I think there's a real big tooling gap because we're dealing with really large volumes of data, and oftentimes the data that went through inference doesn't get persisted in any way. And if you are trying to answer the question of what happened yesterday, what was the distribution of my features, if you're doing this data-centric debugging approach, oftentimes what you'll have to do is replay the entire thing, reproduce the entire thing for that day in order to answer that question. Or another kind of complexity that comes in place is if the data that your system is processing is highly confidential and your operator, like machine learning engineer who's just in the ops team, doesn't have access to that highly confidential data. For them, answering that question becomes then kind of a wild goose chase of getting access and permissions. So I think the real big gap is figuring out how to maybe get inspired by some of the sophisticated DevOps systems that keep track of a lot of artifacts and metadata that capture the health of the system and the state of the system at any given point. So you can easily go back and get at least a vague understanding of what was happening yesterday or last hour or last week.
Yeah, no, I mean, definitely. And that's what we have been trying to promote with Metaflow as well. And I think that's super powerful. But overall, to answer the question that like, where are the gaps? I think that there are like gaps everywhere. So I think always the kind of the way how I've been thinking about the question is that, is there something different in your process that you would do differently if you, let's say, had only 10 megabytes of data? And like if you feel that the process would be very different, or you could be doing so much more if you had only 10 megabytes of data, then it clearly signals that it's a kind of a scale problem and like it's a tooling problem. And like quite often, like for instance, the iterations are just way too slow. And the fact that like you can't compare different models, you can't reproduce things easily because things are just like way too slow or cumbersome. I mean, that's definitely a signal that there are gaps in the tooling and in the infrastructure. And that's hopefully something that like we can technically fix over time.
Yeah. Alessya, I know that you and your team have spent a lot of time working on kind of proactive alerts around machine learning in production. Like, what are your thoughts on like the differences between production ML debugging versus like training ML debugging?
I would say there are a lot of similarities, and ideally, it's kind of the same pattern as your training environment and your production environment for feature extraction or for model serving. The more similar your tools are across these two paradigms, the better, because the more familiar you would be, and kind of you would be forced to use the same techniques for debugging, training, and production pipelines. I think the big difference is in production. Your data itself is constantly changing just by the nature of that. So recognizing how that affects your systems is really hard, and oftentimes that's what majority of the debugging is focused on. So identifying, I think as Adrian was mentioning, like making sure that if you're recording stuff on devices, if you can't potentially persist all of the raw data that you have seen, recording as much information as possible about this data in your production inference pipelines becomes very important and very, very difficult to do, because you are inevitably dealing with, there's this shift where you're probably starting with a lot of data for training, and you have to scale out your system to accommodate a lot of training data, because the more data you have, the more accurate is your model. However, after some amount of time that your system has been in production, I think that shifts, and you are all of a sudden sitting on potentially months or years of the raw data that you have been processing, and at that point, if you haven't been carefully storing it and taking good care of how it's cataloged, then you're sitting on some cold storage of terabytes of data, and you don't even know what to do with it and how to use it for any good purpose. So I think thinking about kind of those two paradigms becomes very important.
And given how important kind of, or the thing that's unique about machine learning is like the data distribution drift and like the problem domain that your model's running on, it's kind of slowly evolving over time as different people use it. Like, how should your debugging kind of ML monitoring systems like take that into account?
Well, I think one of the interesting aspects about machine learning debugging that doesn't come into play in like traditional software debugging is it's important. It often becomes important to involve an SME, like subject matter expert, that maybe understands how the problem that you're solving is solved without machine learning. I think like in medical devices, this becomes very important because as a machine learning engineer, or machine learning scientist, you're building a model, but you maybe have seen an X-ray like twice if you know liked snowboarding and ended up in the ER, unfortunately. But otherwise, you don't understand what X-rays are, what are they capturing. So when you're debugging, it's important to make the tools accessible and understandable by non-technical SMEs that can come in and help you understand, you know, what are you missing, and making sure that your model is performing according to your expectations. And I think that's probably one of the trickiest aspects of machine learning debugging is making some of these tools for surfacing how the model is performing and what exactly is it doing on particular examples to subject matter experts that potentially do not understand how the model work, but do need to inject their knowledge into debugging.
Thanks everyone for taking time to chat. I just want to give everyone a chance to kind of give any like quick closing thoughts or closing takeaways. Chun, do you want to start off?
I always have the dream of like pushing all our ML platform and tools to kind of like consumer facing level, and that's like the thing I'm really passionate about. We talk about like different like ownership, shareholders, different like collaborations, and different gap between like a data and ML platform, and gap between like training and like production level like debugging. So yeah, it's really excited to hear everyone's thoughts here, and then like I think we have so much to do, and then pushing all the tools to the next level to make it more accessible and like more explainable will be the thing we keep working on.
Alessya?
I think it's very exciting that there's kind of this new focus in our community on the tools that would make our systems more robust and more reliable. I'm really excited to be hearing these data-centric approaches because I think that whole area of thinking has been really underserved. So really love the conversation today. And one thing, maybe a little bit self-serving, we talked quite a bit about logging, and one of the things that my team at WhyLabs has put out to the open source as a logging library that deals with different data modalities in a really lightweight manner, focusing just on extracting statistics. And what I find exciting is having collaborators from different kind of fields of machine learning chip in and give feedback, especially from, you know, the field that deals with on-edge or on-device learning. So we'll be really excited to have more of the community come in and give feedback on the approaches that we're taking with the library. It's called WhyLogs, and it's available on GitHub.
Awesome. Adrian?
Yeah, definitely really enjoyed the discussion, and it was great to hear different perspectives. I think, you know, we talked a lot about the kind of recording and ingestion of data. That's something that we're really excited about at Foxglove. I think, you know, other things that I would emphasize, just the tooling is so critical to get right to make ML engineers productive. I think that, you know, I've seen time after time people just struggling to find data that's relevant to them, struggle to get it into the right place. You know, if you don't have your data set up and indexed and cataloged and in the right places, then people not only spend a huge amount of time kind of writing their own custom jobs to go and find this data, but they also can waste a whole lot of money on compute very easily if you're kind of you know, you haven't properly kind of denormalized the structure of your data. If you've got, you know, if people need to go through terabytes or petabytes of data and cross-reference different pieces of information to even find, you know, a bunch of samples in some geolocation or some time range or some particular set of events that were happening. So yeah, again, I just kind of would emphasize how important it is having kind of the data structured and then making the you know, the tools really accessible to people so that ML engineers can and ML scientists can focus on building high quality models and debugging high quality models without kind of, you know, writing their own software to extract data.
And last one is Ville.
Well, I mean, yeah, no, I mean, definitely like +1ing what Adrian was just saying about the importance of having ML tooling. Well, of course, I mean, that's what we are developing, and like we believe that that's very important. I think like the couple of like main things that we believe in is definitely having these stable environments. I think that this is the very nature of doing any kind of a data-centric development, data-centric programming, that you can really control the environment. You can have a very structured, like good process for like running these different experiments, and also like making sure that those iterations are fast enough. So you have the compute layer, you have the compute capacity, you have a data layer that can supply data fast enough so that like you are maximally productive as a data scientist or machine learning engineer, like when going through these iterations. And then the other part is definitely the production. And like when you are in production, like you have the monitoring best practices, and also what Alessya was saying before about being able to monitor the deltas over time. I mean, it seems like table stakes. I mean, that goes surprisingly far. But at the same time, I know that like today, of course, I mean, like we are still missing like much of the tooling. So it's easy to say that these things are important, like actually like making it work in practice still takes quite a bit of work. So, but yeah, at least we roughly know, like it seems that we roughly know like what are the right ingredients. So.
Awesome. Well, I think that's probably about a wrap, but I want to thank everyone so much for joining us, and thank all of our speakers for coming in and sharing their perspectives and some of the experiences that they've worked on in the past.
Thanks, Elliot.
Thank you.
Thank you.
Thanks.